Today we're looking again at static rigid bodies, but we're just going to focus in specifically on one type. We're going to look at our ladder type questions. Now, what specifically makes something a ladder question is that the static rigid body is supported at its two ends. Usually one is on the ground and one is against the wall, but the supports, the points of contact, are the two ends of the static rigid body. So a reminder of the force diagram that you're going to need to produce with this. We're going to need to think about the force that's generated by the mass of the static rigid body. That's usually going to be mg, unless we were given the weight to begin with. And then the force from the contact points. So R is going to be the normal reaction on the ground, and S is the normal reaction at the wall. And in both of these cases, there may or may not be friction. So these two red forces that I've drawn will depend on whether the ground was rough or smooth, whether the wall was rough or smooth. The most common combination is rough ground, smooth wall, but as always, paying attention to detail when reading the question will help you to make sure you produce this model correctly. This is the most basic version of the diagram you'll have. There may be additional forces on here. There may be lengths that we do or do not know. All of that is going to come from the context of the question. So we have a ladder question, and we've been told that a uniform ladder AB of mass 17 kilograms and length 18 meters rests against a smooth wall with its lower end on rough horizontal ground. There's a lot of information already in that first sentence. So let's just start with our diagram. AB, that's the ladder. It's resting on rough ground. So straight away I can put in my reaction force and I know that there's going to be some friction. We know that friction is always opposing motion or potential motion. Let's imagine this ladder. If it was to slip, it would slip away from the wall. The base of the ladder would move away from the wall. So we know friction is in the opposite direction to that potential movement. So I model mu r towards the wall. We know there's a reaction force on the wall. Since the wall was smooth, there's no friction there. We were told the mass of the plank is 17 kilograms, which means the weight is 17 g. We were told that this was a uniform ladder of length 19. So we know that the weight is modelled in the middle, which means we have 19 over 2 from A to the middle, and we have 19 over 2 from the middle to B. So there we have our diagram complete and ready to start. The next sentence tells us that the ladder rests in equilibrium and that is elevated at an angle of 50 degrees to the horizontal. So I can get that angle on the diagram as well. Now, with all static rigid body questions, we are pulling together a lot of skills that we've used so far in our mechanics course. We're using the fact that we know that this is in equilibrium, but it's a static rigid body. That means it's not moving and it's stationary. If it's stationary, that means that its resultant force in any direction is going to be 0. So we know we can resolve vertically and it should equal 0. We can resolve horizontally, it should equal 0. Even taking moments in any direction, the resultant moment should equal 0. We're going to bring in friction, we're going to bring in the coefficient of friction, maximum friction, and limiting equilibrium. All of these concepts and skills are going to need to be at play within the same question. You're going to encounter some meaty questions that are expecting you to be proficient in each of these different concepts and techniques. So let's get into it for today. So this question's asked us to firstly find the magnitude of the normal reaction S at the wall. So to find S, I'm going to want to do one of two things, either taking moments or resolving horizontally, since S is a horizontal force. At the moment, resolving horizontally wouldn't be useful. I know S is going to be equal to mu r, but I don't know either mu or r at the moment. I'm going to start by taking moments. If I take moments from point A, we already know that the forces going through A will not be considered. So I don't need to worry about r, which is unknown, and I don't need to worry about mu, which is unknown. The only forces I'm going to work with are the 17g and s. Both of these are known. The lengths that I would use to get there are known, and the angle is known. So that's enough to form an equation to solve for s. Let's be really careful with the equation that we're forming. Starting from point A, let's first focus on 17g. So this is the force, and this is the distance to get to the force. As we've seen before, to calculate the moment, we want the perpendicular distance to the force multiplied by the force. In this case, the perpendicular distance is the dashed line. That is going to be 19 over 2 cosine 50. The hypotenuse of this triangle multiplied by cosine 50. That's the distance from A to the force. That's the perpendicular distance from A to the force. So the moment is going to be 19 over 2 cosine 50 multiplied by 17g. So that's a clockwise moment. The second moment we're going to find is the anti-clockwise. So I can say that this is equal to the moment generated by S. Let's have a look at that moment. So there's the force. We want the perpendicular distance to that force. We ignore everything else from the diagram. This is what we're focusing on. I want to know the length of that dashed line. Well, the hypotenuse of the triangle we've drawn so far is 19. The dashed line we're looking for is the opposite side within this triangle. So we'll be using sine 50. And we just need to multiply that by the hypotenuse. Well, the hypotenuse length is 19. So 19 sine 50. The moment is 19 sine 50 times s. Got a nice equation that we can just rearrange and make s the subject. We know from there s is going to equal 7.13 g or 68.9 newtons to 3 significant figures. So there we go, we've found s. In part B, we're asked to find the magnitude of the normal reaction at the ground and the frictional force at the ground. So to do that, we need to resolve horizontally and vertically. Let's start horizontally. So S equals mu r. So the frictional force on the ground, mu r, is going to be exactly the same as S, which we just found. So the frictional force at the ground is 7.13 g. The reaction force R we can find by resolving vertically. There's only two vertical forces, and we know that R, which is up, must equal 17g, which is down. R equals 17g. Now that we know this, we can finally find the coefficient of friction. We can find mu. Just substitute R into our earlier equation, rearrange for mu, just into your calculator, and mu to 3 significant figures, 0.420. And that's what we would expect in a ladder question. So this is a basic entry-level ladder question. We took moments, we resolved vertically, we resolved horizontally, and that was enough to solve for all of the unknowns. We only really had 8 lines of working out. What really made the difference is a very clear, well-structured diagram which came from reading and interpreting the context correctly. Okay, so let's just try one more, which is a little bit more involved, and you'll see why. So, this time around, we're told that a ladder AB of mass M and length 3A has one end A resting on rough horizontal ground, the other end B rests against a smooth vertical wall. So straight away you can see here that the mass is unknown and the length is also unknown. So we're going to have quite a few unknowns that we're working with. We're going to need to really trust our algebra skills and be very careful as we rearrange and simplify expressions in front of us. Starting on the diagram, here's the ladder. A and B are on the ground and on the wall. We know that the weight is mg. A reaction force on the ground is accompanied with friction since it was rough ground. We also have a reaction force on the wall, which we'll call P. If we keep on reading, we're told that the other end B rests against a smooth vertical wall. So there is a reaction force on the wall, but there is no friction. We'll call that S. We're then further told that a load of mass 2m is fixed on the ladder at point C, and AC is A. Well, apart from the diagram that we've been given, I would know that C lies in between A and the middle because the length of the ladder is 3A, half of that is 3 over 2A, and this is only 1A. So I'll place C right here, and there's a force of 2 mg. Okay, I've got one length on the ladder so far. We know that AC is A. We're told that the ladder is modelled as a uniform rod, so we know that the weight is exactly at the middle of the ladder. Well, if the length of the ladder is 3A, then halfway of the ladder is 3 over 2A, or 1.5A. So I can actually label some of these other lengths as well. Here we have half A, and here we have 3 over 2A. And lastly, we were told that the angle was 60 degrees with the ground. We're asked to find the coefficient of friction between the ladder and the ground. So let's go ahead. The coefficient of friction between the ladder and the ground is mu. Just like in the previous question, we need two things to find mu r. We know that mu r is going to be the same as S, is going to be the same as the reaction force coming out of the wall. That's not enough. I also need to find r. So I can cancel out r and I'll be left with mu. So we'll go through and start in the same way that we did before by taking moments from A. So we'll just take those forces in order, moving away from A. First, we're going to consider the 2 mg force. Perpendicular distance multiplied by the force. The perpendicular distance here, the dashed line is an adjacent to the angle, so we're going to be using cosine 60, and we'll multiply by 2 mg. We'll move on to the second force. We're looking at mg. The distance along the ladder is 3 over 2. The dashed distance, perpendicular distance, is going to be 3 over 2 A cosine 60. And we'll multiply by mg to make it a force. So these were the two clockwise moments. Now we're going to add in the anti-clockwise moment. So here it is on the diagram. We know that the hypotenuse is going to be 3A. We want to know what that dashed distance is going to be. It's opposite the 60. So this dashed distance, the perpendicular distance from the pivot point to the force, is 3A sine 60. And we're going to multiply that by S. So there's the moments equation. We know that this is true. We want to rearrange and make S the subject. If we rearrange carefully enough, we'll notice that things will cancel out and simplify, and we'll have something nice to work with. I'm going to start by factorizing and taking out AMG. Then I could tidy up inside the bracket, but I'm happy to write that into my calculator. We're going to divide by 3A sine 60. The A's cancel out immediately. I'm going to keep it in terms of mg, so I've really just got the bracket in the numerator divided by 3 sine 60. So S is going to equal 7 over 6 root 3 mg. Okay, now I've got a value for S. I'm just going to try and find a value for R. We can do that by resolving vertically. Here are the three vertical forces. Up is going to equal down, so R is going to equal 3 mg. So now I've got a value for S and I've got a value for R. I can resolve horizontally. Resolving horizontally says that mu R must equal S. Mu 3 mg equals 7 over 6 root 3 mg. Mg's are going to cancel. I've got 3 mu equals 7 over 6 root 3. From there we see that mu is 7 over 18 root 3. And if we want that as a decimal, we get 0.225 to 3 significant figures. So even in this question where the mass of the ladder was unknown, the mass of the particle added was unknown, and the lengths were unknown, we could still follow exactly the same technique, producing a well-constructed and annotated diagram, and then we did the three things we always do. We took moments, we resolved vertically, were resolved horizontally. And that gave us exactly what we were looking for. So with that, I'm going to leave it to you to get some practice. Use these 2 example questions as a model, and you should be able to access just about any ladder question that comes your way. Be careful in reading the context of the question. Do you have rough ground? Do you have a rough wall? Do you have a uniform ladder? All of these things can subtly change the whole question that you're working on. Okay, Teresa, and we're just about finished. But before you move on to some practice questions, let's take a quick look at the specification that's on the screen and exactly what it is that students are expected to be able to show, exactly what the examiners are anticipating that you'll be confident in. While you read through that, I want to quickly remind you that it would be sensible for you to come back here and re-watch this video at a later date. Maybe you're coming back in 2 or 3 weeks, or right before an assessment as a refresher. As you watch through the second time round, because you've done your practice and you've experienced these questions for yourself, you've experienced a bit of problem solving for yourself, a lot of what we go through here should resonate with you so much more. And you get the chance to really embed your understanding of the difficult concepts. That'll be anything that I've flagged with the A-star.